Hey guys, welcome back to GenIgnite X. This is Pushkal Bhatia. Big thank you if you were already here and a warm welcome if you're here for the first time. If you watched our last video, you know RNNs are awesome for stuff like sentences or time series, but they have the vanishing gradient problem where they basically forget everything that's happening early in a long sequence. Feedback just kind of fades away. So today we are fixing that. We're fixing that with LSTMs. LSTMs stand for Long Short-Term Memory Networks. This is the video where we really dig into how they work, super beginner friendly. You'll also go through tiny little bit of mathematics because it is important that you understand it that much. We're going to use simple pictures so that you have that in your head, everyday analogies, and one full sentence example so you can actually see the memory moving along. No scary math overload, as I said, but just enough so it makes sense. With that, let's get started. So let's start with the big picture. Alright, look at this diagram right here. This is what one step of an LSTM looks like. One movement when it's reading one word. Remember, like RNNs, LSTMs are sequential, one word at a time. That's how they process a big sentence. You see that big horizontal line going straight across the middle? That's called the cell state. Picture it as a conveyor belt that carries important long-term memory from the very first word of your sentence all the way to the last word. In regular RNNs, the memory gets completely overwritten and then crushed every single step, like scribbling over the same post-it note until you can't read anything, right? But in LSTMs, this conveyor belt keeps rolling forward, mostly the same, and they're like three little gates that decide exactly what gets kept, what gets added, or what gets shared. That's what we'll try to dig into. That's how we'll try to understand how LSTMs work. These gates are like small valves, right? Like small little switches or traffic cops, right? Each one looks at two things. One, the word we are reading right now, we call it XT. It's just the current word that's turned into numbers. The numbers are like embeddings, right? You'd have heard it a lot of times. Embeddings are just vectors of numbers. The second, what we're thinking about from the previous step, we call it HT-1, or that is our short-term memory. The gates use two squashing techniques. First, the sigmoid. It squeezes any number down to between 0 and 1. 0 means no way, forget it, hide it, throw it away. 1 means yes, keep everything, show me everything you've got. 0.5, for example, is somewhere halfway. Think of it like a dimmer switch, right? Or a volume knob, which has the range between 0 and 1. The second is tan H. This squeezes the number between -1 and +1. So positive means build up or strengthen. Negative means correct or reduce. Close to 0 means barely touch it. It's good whatever we're getting. Now let's make this real with a sentence we'll follow throughout this video, the whole way through. Let's see this sentence. The cat sat on the mat because it was tired. Now we want the model to figure out that it refers to the cat, even though mat is closer, as you see in the sentence. LSTMs are great at this long distance connection, hence long short-term memory. Let's see how each gate handles this. First, the forget gate. What's its job? Well, its job is to decide which parts of the old memory sitting on the conveyor belt that we talked about should be thrown away or faded a little bit so that the belt doesn't get jammed with useless junk. Now, how does this work? It takes the current word plus what we remembered from the last time. runs them through some learned dials. Now, what are these dials? These dials are these impedances or the weights, the numbers that model tunes with training, something that we talked about last time. And then it adds a tiny bias tweak. Again, if you don't know what bias is, we did talk about it last time, so go and feel free to see the video. And then it squeezes everything with sigmoid so that it gets a value between 0 and 1. Now those 0 to 1 numbers then multiply the old cell state, element by element. So 1 keeps the piece of memory perfectly without changing a thing. 0 erases it completely, taking into account nothing. And a number like 0.7, for example, fades it a little bit. Think of it like going through your closet, right? This is an old hoodie. Keep it forever. That's 1. Oh, these socks have holes? Well, they're not of use anymore. Just toss them away. Maybe keep them for now. We'll see. Maybe we can stitch them. That might be a value like 0.6. I'm just trying to connect this to real world cases so that you could actually visualize and understand how this happens. Now, in our sentence, when we hit the cat, forget gate says close to 1 on everything about cat. We really want to keep that subject. When we get to sat on the mat, it might fade away tiny unimportant details like exact sitting position, but it keeps cat at almost 1 because we still need that. Because it was tired, forget gate is still protecting cat word strongly. If it had faded cat word too much, then it in that sentence, it word in the sentence would probably point to mat by mistake, which is what we don't want. And that's the job of the forget gate. That's the forget gate, the eraser that keeps the belt clean but protects what matters. Next is the input gate and the candidate. These two work together. Now what's their job? Well, their job is to decide what brand new information from the word we're reading right now should get added to the long-term conveyor belt. The forget gate forgets. This one decides what to keep in the new thing that we're getting. How does it work? The input gate part does the same thing as forget. The current word plus the previous short-term memory, then comes the weights, then comes sigmoid, and then comes 0 to 1 values. This says how much of this new stuff should we actually let in. 0 is equal to ignore the word completely. 1 equals add everything that's useful. The candidate part, sometimes drawn as a separate box, takes the same inputs, different weights and tanh, that's the bigger difference, and then splits out the values between -1 and +1. Tanh basically does that, which splits the value from -1 to +1 as compared to your sigmoid. This is the actual new content we might add. Positive to strengthen something more, negative to correct or weaken something, and 0 to barely change anything. And understand this, because if it was just sigmoid, then we would always just add more information. Because tanh can add values from -1 to 1, we can use that to correct stuff. We can use that to tweak stuff in a positive or a negative way, or we could be close to 0 to just accept whatever we are getting. Then we multiply the input gate, how much, by the candidate. That gives us a nice controlled updated packet for this entire process in the second phase, which is the input gate. Let's go back to our analogy. Adding to a shared grocery list of the fridge. Input gate decides how big should I write this. Candidate decides something like add more milk, that's plus, or remove the expired yogurt, that's negative, or neutral, just be at 0. Now in our sentence, at the cat, like the cat, input gate is high, say 0.9. Candidate is positive, we add strong cat is the subject info to this belt. Add because it when we reach because it in the sentence. Input gate goes high again because pronouns are important. Candidate helps reinforce the link. At tired, input gate high, candidate adds the tired description. It's a quick side example to show why negative matters. I thought this movie was amazing, but honestly, it was awful. What's happening in this sentence? Early on, the candidate adds positive sentiment, but later, candidate adds negative, subtracts from the total. Without tannage, negatives would basically be stuck saying the movie was amazing forever. And that's how the input gate and the candidate work together. Now here's the most important part, the actual update to the cell state. This is what makes LSTMs special. After forget gate has faded or kept the old belt contents, and after we've made our new updated packet from the input gate and the candidate, we do this. New cell state is equal to our old cell state after forget fading plus the new updated packet. Now, I've written down these formations in some of the images that I'm sharing, but visually it's written like CT, which is our cell state, is equal to forget FT into CT minus 1 plus input IT into C cap T. So first, multiply by forget, fade or keep old stuff, and then add the new control info. Let's take another example. I love giving examples, and that's where I want to make this different so that you could actually understand concepts pretty well. Think of your bank account balance. So you might fade out or like subtract some forgotten smaller transactions, and then suddenly you add today's paycheck. The balance keeps going forward with precise changes. Nothing here, is getting crushed. This addition is the magic because it's plus instead of just multiplying everything. The learning signals don't vanish when they travel back through time. That's why LSTMs can remember things from 100 words ago. And that was one of the biggest concerns with RNNs because of the vanishing gradient problem. They were good at keeping very short memories. If the sentence is not too long, it would do good. But when it comes to like a really long sentence, maybe paragraph with 100, 150, 500 words, it couldn't do a great job. And that's why LSTMs with these additive instead of multiplicative calculations helps eradicating the vanishing gradient problem. Back to our sentence as I promised. So after the cat, cell state has strong cat info added. After sat on the mat, forget fades tiny junk, then we add position info on top. Cat memory is still strong, now in fact richer. At because it was tired, forget gate keeps cat word protected. Input adds linking tired info on the top. So the early cat word that it had captured is still sitting there strong because we only added, we didn't override. So when the model sees it finally, it knows that cat is still the main thing on the belt and it's not mat. That's how the cell state gets updated. Last one is the output gate. So what's its job now? From everything that's now on the conveyor belt, decide what to reveal or share right now as the short-term output. This is what we call as HT. This is what gets passed to the next step or used to make a prediction. So how does this happen? Sigmoid on the current word plus previous short-term memory, again 0 to 1 values, saying how much of the belt do we show. Then take the current cell state, squash it with tanh so the numbers stay reasonable, multiply it with the sigmoid amount, and boom, that's your new HT. Another analogy for this, right? So you have your full diary, that's your cell state, but you only read out the relevant page to your friend at that moment. That's what we are doing here. Going back to our sentence example, it was tired, output gate opens wide on the cat related parts of the belt. The model confidently says it now points to cat and not Matt. All these gates learn their jobs during training. This is something, again, we've talked, when we talked about the single neuron, when you were talking about a neural network, we talked about RNNs, but all of these gates learn their jobs during training. The model guesses wrong, it calculates the error, sends tiny nudges back to adjust the weights, so the next time the gates make better decisions about forgetting, adding, revealing. The additive update keeps everything stable. So each of your gate and the candidate has weights associated with them. When the cell state or when the entire cell is making prediction, it gets something wrong, it back propagates, all of these weights are updated, and over trillions, millions of examples, the weights are finally set to something that makes the prediction right. Those are all the gates, and that's your LSTM in a sense. Before we close, there's a quick bonus. LSTMs got even stronger when people put them in encoder-decoder setups. Now, encoder-decoders are actually very important because that also acts as the base of transformers, which we'll be learning in the next video. Encoders read the whole input sentence step by step, building up that cell state conveyor belt. At the very end, the final cell state plus the hidden state becomes one field context vector. It's like the summary bottle that holds the meaning of everything. And encoders, decoders in general are just neural networks, and they're not just only applicable to LSTMs. It's just that the LSTM's architecture can then further be made stronger. And in a similar way, we'll learn in the next video how they use in transformers. And then the decoder starts with that bottle, then generates the output one word at a time, feeding its own previous word back in until it says done, right? So let's take that example again, right? You feed in, the cat sat on the mat. The encoder with many layers, hidden layers, etc. Hidden layers is something we talked about in the last video, summarizes. The decoder spits out the French version word by word, handles different lengths and orders. Though super long sentences can lose some early details in that one summary bottle because it's kind of summarizing everything, right? So that was encoder decoder. Just wanted to give you a very broad overview. We could talk about more about this in the next video too, but that will be the basic of transformers. That's LSTMs in a nutshell. Conveyor belt memory, 3 gates controlling forget, add, reveal, and additive updates that stop forgetting. So which bit clicked for you? The belt idea, how we add new stuff without overfitting the it, referring to the cat example, or just the encoder decoder thing? Drop it in the comments. If this made sense, hit like, subscribe, and turn on notifications, because in the next episode we will go through the understanding of transformers, why LSTMs also were not the best in the end, and why transformers came to revolutionize AI. See you then, take care, bye bye.